This screencast is going to focus on acid-base titrations, and it'll actually be broken up into 3 separate screencasts. We're going to go through each scenario, of which there are 3, and we're going to start this one with the strong acid and strong base case. And this is one that you're familiar with because in first year chemistry you did the typical sodium hydroxide HCl titration, and then we also did it earlier in the year when we did some acid-base chemistry in AP this year. And so the strong acid, strong base case, when you think of neutralization, you obviously think of a pH of 7. And this is the only scenario where you will end up with a pH of 7 at the equivalence point. And the reason is, if you look at this net ionic equation, this comes from the strong acid, the OH minus comes from the strong base, you make water. That's actually the reverse reaction for the autoionization of water. And we have a Kw for that, which is 1 times 10 to the negative 14th. So if I wanted to know, and it's missing the little reversible right there, but if I wanted to know what the K for this reaction was, I would just do the inverse, 1 over. And you notice that you see this very, very large K. And so that tells us that that's a reaction that's going to go to completion. So it's very easy for these guys to get together and form water. So the answer there is yes. So anytime you have a strong acid and a strong base, it's really a stoichiometry problem, not so much an equilibrium one because it goes to completion. Now we want to be familiar with titration curves, and I feel like you've seen these before. You saw them last year kind of in passing, and you've experienced it in lab as well, because what happens is, for this scenario, you would have HCl sitting in the flask, and you'd have an indicator, phenolphthalein, and we know that it's clear when the pH is less than 7, and we know that it turns pink when the pH is greater than 9, basically, and then you've got kind of that wiggle room there. And so here you are in lab, you're adding your base, you see a little bit of pink, and then it goes away. Yeah, a little bit more sodium hydroxide, gets a little bit pinker, and then all of a sudden you add what seems like a tiny, tiny little drop, and you see this huge increase in pH. And then after that, anytime you add the base, obviously this is pink here, it's clear here, and it just takes a tiny little bit of base to change the pH pretty greatly. But you'll notice, since this is marked as the equivalence point, the easiest way to find it is to find the steep part of the graph and just estimate at the middle. So that's why they've marked it here, and the pH is indeed 7. So this doesn't just apply to NaOH, but anytime you have a strong acid and a strong base, the pH is going to be equal to 7. So we'll run through the math. Before we do that, there's a new unit, and it's not really a new unit, but it's using the mole as a millimole. So if you think about molarity, molarity is moles over liters. And so sometimes some of y'all have gotten into trouble because you've tried to plug in milliliters here, and you obviously don't get the right ratio. However, a millimole is 10 to the negative 3rd moles. And so if you take a millimole and divide it by a milliliter, you get molarity as well. And if you think about it, it's because milli and milli cancel, and you end up with moles per liters. Now, if you don't want to worry about working it out in this unit, that's fine, but I will work it out in millimoles because it just tends to make the math a little bit easier. So what we're going to do is we're going to watch how the pH changes as we add Okay, sorry about that little interruption. Basically, I started working this problem out as if the HCl was in the flask, and if I had actually read the problem, I would have seen that the HCl is actually being delivered to the sodium hydroxide, which is a little bit different. Regardless, NaOH is a strong base, so it'll break up into Na plus and OH minus. So if this is 0.150 molar, I know that this is 1 to 1, and so the POH is just the negative log of 0.150. So that comes out to a POH of 13.18, which we can, a POH of 0.8239, which then can be converted to a pH of 13.18. So sorry about that. So the pH starting is 13.18, which makes sense for a strong base, that it's much, much greater than 7. Okay, so now what we're going to do is we're going to add 4 milliliters of acid, and we're going to recalculate the pH. Now we would expect the pH to drop, and so if we don't get a number that's less than 13 point, should be 08, 18 or 08? Nope, 18 was right. Okay, sorry about that. Alright, so basically anytime you have an acid-base titration, it's a balance between the millimoles of the OH minus and the millimoles of the H plus. Alright, so to figure out starting millimoles of base, I just take my molarity and I'm going to multiply it by the volume of base present, and so that's 50 milliliters. And so I get 7.500 millimoles of base. To get my H plus, the concentration of acid is 0.250 molar. I've delivered 4 milliliters, and so I've added 1 millimole of acid. Alright, so if you think to yourself, well, what is the definition of neutralization? It's when moles of acid equal moles of base. So if you want to know, am I at the neutralization point, the answer is no, right? Because our OH is in excess and our H plus, there's only a little bit of it. Alright, so what we want to do is we want to take the difference between how much base there was to begin with and how much has been neutralized by the acid. So if you subtract these two, you see that the OH is in excess by 6.5 millimoles. Now, it's a strong base, so it's fully going to ionize, but the thing that students forget is that now the total volume is how much? You had 50, you added 4, so the total volume is now 54. So you've got to dilute what's present. So to get the OH minus concentration, you take the 6.50 millimoles and divide it by the 54.0 milliliters. So that step is the most commonly forgotten step. So we get 0.120 molar. So to get a POH, we negative log that, and we get 0.919, and so the pH is 13.08. So we were starting at 13.18, we added some acid, we're down to 13.08, certainly moving in the right direction because it's become more acidic, but certainly not near the equivalence point. Alright, so now we've added 29.5 milliliters. So we know that the millimoles of OH minus, and again, each time you go back to the starting. So we're still going to say that we started with this much base. We did that calculation up here. So now we're going to find millimoles of H plus. And we're going to do that by saying the concentration is 0.250. The volume added is 29.50. So now the millimoles of acid is 7.375. So now we're really approaching the equivalence point because we're almost to the point where moles of acid equal moles of base. But again, what's still in excess? The OH is in excess. And so we subtract those. The amount of OH that's present now, we just take the difference. So we subtract 7.5 and 7.375. And we get 0.125 millimoles of OH minus. But the total volume now is 50 plus this 29.50. So total volume is now 79.5 milliliters. So we dilute that, we get a concentration of 1.57 times 10 to the negative third molar. So the concentration of OH is really, really small. So we get the POH by doing the minus log of that number. POH comes out to 2.80, pH 11.20. So even though we're right before the equivalence point, and again the reason we know that is because these guys are approaching being equal to each other, right? We're still at a pretty high pH. And so pH is 11.2. So if we were kind of tracking this, like on a titration curve, we would be high and we would be getting a little bit lower pH as we're going. So now we're about to see the big change. So millimoles of OH, again, same starting conditions, so 7.5 millimoles. Millimoles of H plus, still 0.25 molar. We've added 30 milliliters now. And so the millimoles of acid is 7.50. So what's special about this when moles of acid equal moles of base? Moles of acid equal moles of base. We are at the equivalence point. Okay? And so if I subtract 7.5 from 7.5, I get 0 millimoles of OH. I also get 0 millimoles of H plus. And so that means at the equivalence point, the reaction that's dominating is this one. It's the only reaction going on. And so we know the pH is equal to 7. And that will only be true for strong acid, strong base. It will not apply to our weak cases. Okay, so go back to our little sketch of our titration curve. Now the pH is dropped to about 7. So now we're going to go past the equivalence point and see what happens. So again, just a half milliliter difference here, right? Before the equivalence point and now after the equivalence point. And we'll see what a big difference it makes in pH. And that way you'll kind of see why it's so hard to get that nice, pretty pink when we're doing titrations, because just a tiny little drop makes a huge difference in pH. Alright, so H plus, still 0.25 molar for the acid. Now 30.5 milliliters. So millimoles of acid is equal to 7.63 millimoles. Okay, so now who's in excess? We have 7.63 of the acid, only 7.5 of the base. So the millimoles of H plus is in excess. So now this guy's winning, right? So if I want to find the pH, I take the difference in those two. So I get 0.13 millimoles of H plus. Don't forget to divide by the total volume. So 80.5. We get a concentration of H plus now to be equal to 1.61 times 10 to the negative third molar. So we negative log that number. It's not a two-step now because the H plus is in excess, right? And we get a pH of 2.79. So look at that, a half a milliliter, and now we're all the way down to 2.79. Alright, so steep little drop. Okay, and now we're going to be way past the equivalence point. Millimoles of OH minus, starting at 7.5. Millimoles of H plus. Concentrations 2.50. We've added 40. We get 10 millimoles of H plus. So 7.5, who's in excess? This guy's in excess by 2.5 millimoles. Divide it by the total volume, and that's going to give us the concentration of H plus. So we're going to take 40 mils, add it to 50. We've got 90 milliliters. So our concentration of H plus comes out to 2.78 times 10 to the negative 2. So pH, we're just going to minus log that number, and pH comes out to 1.56. Okay, so we've added some more, and now it's just going to decrease. It'll be our little sketch for our titration curve.